substitute, if they substitute in here, right, then they get, did I do that right? Maybe they do it the other way. How do they do it? They solve for omega squared. Well, what does it say? We divide 17 by 15, so they just divide the whole equation. Okay, they divide this into that. And when they divide it, they get a over x, and they, okay, so this cancels with that. When they divide this equation into that. And so they divide both sides, you get ax over a0, and there's a minus sign, they put it in here, omega squared, they take the square root, and they wind up with 23.5. Well, that's a little bit tricky, huh?
So,
Yeah.
I think that they substitute x on omega on acceleration. As you see, we have x0 equal xm cosine phi.
And then they divide through, yeah.
They substitute, it will be at
This
t
becomes
equal.
x0.
Yes, yes.
And then they divide by, okay. All right. And actually, what they said they do is they divide, but either way, it works, right? You can do that, put it here, and then divide by x, or you
Yeah.
said, okay, so. That's pretty clever, because you have three unknowns there. You have x max, and you have c, and you have omega. But anyway, all right, so then they substitute the values that they know, and they get 23.5. So what are the phase and the amplitude? Then they divide the other two equations. There you go. So the phase is phi, and they know omega, and if they divide them, the x's will cancel, and this becomes the tangent, so they get rid of one of them, and they solve for the tangent. They know the other three, and they get minus 4.6, and it has two solutions, I guess. And so they get minus 25 degrees, and then what they do? Then they're solving for x of m in this equation. And it turns out to be minus 0.94. Okay. Or if they substitute the other, phase angle, they get 9.4. I'm sorry, they get plus 9.4. So that's on the other side, right? So in the oscillation, there's two maximums, right? So if you oscillate, if you're oscillating back and forth, there's a solution for this one, a solution for that one. So that's a little clever little solution solving there, but you're all fully capable of that. Okay, that's probably some of the harder stuff there. Okay, what do you think? What do you think there, Mr. Daniel? You remember your algebra? Solving equations, it might be a little tricky. But anyway, I don't know that we get that complicated. But I think those are a couple of good little problems. If you understand, they're probably 90% of the way there for that. Now let's talk about energy. So we're always interested in energy, and we have potential energy, and we have kinetic energy, and we know what the spring, right? The potential energy is how much the spring is compressed, and of course we know the total energy is potential plus kinetic. Here's our potential, here's our kinetic, and you may have done this in the lab. I don't know if some of you might have done this. I think you guys did it. And you got something that was pretty flat, didn't you? Didn't you get something fairly flat?
Pendulum?
Oh, that was the pendulum one. Oh, okay, I was thinking it was a spring. Okay, but it should be similar, but you you got a little bit of dip in there, didn't you? From the loss of energy maybe. Okay, well, for the spring, we know the potential energy is 1/2 kx squared, so they substitute. This is squared, that's squared. And the kinetic energy, 1/2 mv squared, well, we have a value for v, it was omega x squared to negative, sine, we have to square it. And here they substitute k over m for omega squared, so that's k squared m squared. Put it, oh. What happens to the m? Oh, I can't put that in, okay. All right. Okay, so they substitute, and then they add the potential and the kinetic and factor out the 1/2 kx squared. What do they get? They get a cosine squared plus a sine squared, and that's equal to, you'll remember from your equal to 1. Nice little derivation. What do they wind up with? That the total energy is 1/2 kx max squared. Let's think about that for a minute. The total energy is equal to what? It is potential and kinetic, but they added the two and they found out that the total energy is equal to what? What is that? No. No velocity in here. That's the maximum, what?
Potential.
Yeah, the maximum potential. So let's think about that for a second. So we're doing it this way to see it oscillate. As we oscillate, right? Because we're imagining it's this way. But as we oscillate, it has a, it's going up and down, or this way. The potential energy, actually I should say this way. The potential energy is the spring. It's the position of the spring, right? And the kinetic energy is the velocity. So what they're saying is the total energy will be equal to what? The potential energy when it's all the way out at max. That makes sense. Okay. So that tells us the total energy. And that's a really convenient thing to remember, right? If you have an oscillating object, all the total energy is out at the maximum displacement, x sub m squared. All right? Now, it shows us the relationship here between potential and kinetic, one decreasing, the other increasing, the sum always equal to total. All right? So let's take a look. What's this checkpoint? See if we can. Here's a block, has a kinetic energy of 3 joules. Okay. And the spring has an elastic potential energy of 2 when the block is at 2. What is the kinetic energy when the block is at 0? When x is at 0? So we've got a block, right? Here's a block. It's on a spring. All right. You call this x equals 0. We take it out here to x equals 2. Okay. And at that point, the kinetic is 3, and the potential is 2. And the question is, what's the kinetic energy here?
0.
This is the equilibrium point. So what's its speed at the equilibrium point?
Is this 6? because 2 times 3, x times k.
Okay, let's look at this for a second again. The kinetic energy here is 3, the potential is 2. What's that?
5.
Total,
Yeah.
right? So total E is 5. What's the kinetic here? Where's the maximum velocity? Let's see. Where's the max velocity for an oscillation?
Of the symbol.
Yeah, otherwise known as the x equals 0 equilibrium, right? So the kinetic energy at the center, what's the total energy?
5.
The kinetic energy at the center, what's the potential energy at the center? At 0 displacement, 1/2 kx squared, where x is 0. You're a little confused. 0, so the kinetic will be,
5.
yes. Now you're with me. Huh? Threw you off a little bit? Well, that's all right. Are you with me on this one? You get the total energy, and the total energy maintains here, we're assuming no friction, nothing else, okay? Right?
It's a little bit tricky.
This is
A little bit, a little bit, a little bit. U plus K is U plus K, right? Here the total energy U plus K, here the total energy U plus K. What it is, you have to, it takes a while to realize this is max velocity, see, max velocity. So this is 5 and that's 0. But, it's okay though, see, okay, all right. Thinking these things through. All right. What does it say next? What is the elastic potential energy when the block is at -2? So when it's at -2, the potential energy will be what? Here at -2, x equal -2. It'll be what? The potential energy. Carlos, what was it over here? What was the potential energy over here at 2? 2 joules? Huh?
Both positive or not?
It was 2 joules, and what's the energy over here?
Will be 3.
The potential energy. What is the elastic potential energy when the block is at -2? Anybody?
3.
It's 2.
Why do you get 3?
B.
Here's the block, right? This is at the center. Over here, its potential energy is 2,
I just need this.
right? What's it going to be over here?
There you go.
Symmetry?
I thought you needed
It will be 2.
2.
Yeah.
See?
Why is
Energy's-
the difference?
Energy is positive. It's 1/2 kx squared, right? So here, x is 2, and over here, x is -2. But it's symmetrical. Symmetrical. Did that throw you off a little bit? What's throwing you off there? It's symmetrical, see? The energy is symmetrical, the potential energy.
He just needs it sharp.
It's symmetrical. What will the kinetic energy be? What's the total energy there? Potential's 2 and the kinetic 3. See? Is it better or worse? All the way out here at some point, right, at the x max, the potential will be 5, the kinetic will be all the way out.
0.
Yeah, 0. And then on the other side, you see it's symmetrical. Okay? And at x equal minus x max, the potential energy will be zero. Is it kind of making more sense or not, or is it?
It makes sense, but during the exam, please don't give this kind of things.
Why not? Oh, no, we'll have a question just like, something like that. It's, you know, let's talk about it for a second. You know what gravity is, right? mgh. So you start off, I got 10 joules here, I'm halfway, I got 5 joules. Down at the bottom, I got 0. So I drop the potential, the kinetic goes up, right? Conservation of energy, it's the same thing, but what's different? It's symmetrical, right? It's symmetrical, right? Because the spring, in one case you're stretching the spring, in the other case you're compressing the spring. Yes, sir.
When the potential equals the kinetic, is the speed constant?
No.
When does it equal the kinetic?
Well, when does it, you mean where?
Yeah.
We can figure that out. When are they equal? Well, let's see, what's the equations we have?
mgh and then half mv squared.
So, the kinetic is equal to the potential, so the total energy we said was what? 5?
Yeah.
Okay. So, when they're equal, they'll each be
Yeah.
2.5, right?
Yeah.
So where will that be? Well, we said that the total energy, E, is 1/2 kx max squared, right? So, this is 5, and when they're equal, the total energy would be 5, but the potential energy, this is also the equation for the potential energy, the equation is 1/2 kx, right? Squared. And that's 2.5, right?
Yeah.
So what do we get? We get x equal 5 over k, the square root. I don't know what k, did they give us k? They didn't give us k in this particular problem, that was the answer. You see? This is a squared relationship, so it's not going to be in the middle. All right. It's not going to be in the center. It's a quadratic. Right? So if I plot the potential energy, it looks something like that, right? It's a parabola, isn't it? So this is a, remember parabolas from your high school days? Looks like that, see it? Here. The green is, this is the potential energy. So where's halfway? Right there where they cross. So that's not halfway. That's not halfway. Here's the total x. And it's at that point. We'd have to have k to know the exact value. It's kind of making more sense. Okay. Look, how are we doing here? All right, let's see what they're doing here. So you've got a building with a mass damper, which are anti-sway devices that prevent them from oscillating in the wind. The device might be a block oscillating the end of the spring or contracted. The building sways to the east. The block moves east, but delayed enough so when it finally moves, the building is then moving back westward. Thus, the motion of the oscillator is out of step with the motion of the building. So you've got something that oscillates to keep the building stable. Uses a lot in Japan. I think the Japanese are the world's experts in design of these things, being in a